So we were talking about passive and active elements yesterday. And what you're seeing here in this situation is that if I have a passive element, the important thing here is that the passive element does what? Passive element absorbs energy / power from an energy source. In this case, it's going to be the power supply if I only have one in the circuit. Now, if I use the language of energy like we've been talking before, if I was to conceptually look at it, we said that if I have two parallel plates that represents a power supply. Now, note that that's not true, but we could be naive and say that that's what it is. And what I said here is that when a charge goes from a high to a low potential, what the charge is doing is that it's literally losing potential energy. And that potential energy, if I have a resistive element, goes into thermal energy in the circuit. I mean, it goes to some other things, but primarily it goes into thermal energy. So when I say it absorbs power, I really mean that it loses electrical potential energy. But it's electrical potential energy lost as it crosses that element. So now when I go and I look at the element viewpoint, you could see that the high is the positive, the low is the negative. So if a current goes from the positive to the negative terminal, the sign convention is that the voltage is positive and that the current is positive. So when I multiply voltage times current to get the power, we then say any element that absorbs energy / power, its power is greater than 0. So once again, if the current enters the positive terminal, then that element is passive, which means that it absorbs energy from the circuit. Okay, so let's go to the next one. Now the next one is really the definition of an EMF. If I have an active element, then the element delivers energy and power to the circuit. So what do I mean by this? Well, if I draw my picture again, and we've already established from our conversations that this guy represents the high and the low. So when I'm looking at this thing, I got to ask the question, if I have a charge right here, and I want that charge to go from the lower plate to the higher plate, the question is, how do I get that charge to go up? I have to do work. When I looked at this other situation, a charge, a positive charge, naturally moves from a high potential to a low potential. But a positive charge does not naturally move from a negative plate to a positive plate. So the only way I can move this charge up here is if what happens? There's a non-electrical force doing work. Okay, so the only way a positive charge moves from a low to a high potential is if non-electrical work is done. And that, by definition, is the definition of an EMF, right? An EMF, even though they call it an electromotive force, it's not a force, it's actually a potential. So this non-electrical one is the definition of an EMF, and this is really for the most cases. So if you're talking about a battery, so if you're looking at a battery per se, the battery in the EMF is really a chemical potential converted to electrical potential. So you need this EMF in order to actually increase the potential energy of this charge. So picture-wise, what we're really seeing here is that what you're doing here is that somehow, some way, there is some chemical potential here that's being done. So if I was to write this, here is my chemical potential. And what happens to the charge when it gets up here? Well, it has now gained some type of electrical potential. So in other words, what you're seeing here is that you're adding energy to the circuit. So if you're adding energy to the circuit, you're increasing the the potential energy of this charge. So what we're saying here is that the increase in potential energy into the circuit implies this element delivers energy / power. And that, by definition, is active. So now when I look at the element picture, right, we don't care about the conceptual picture, right? So what I just drew here was a conceptual picture. But in circuits, we really don't give a damn about the conceptual picture. What we care about is that we care about let me see if I can get over here, is the element picture. And in the element picture, we have two terminals. So one end of the terminal in this case is negative, the other one is positive. So when I'm looking at this guy right here, the current, look at the current, it's going up the negative. So it's going from the negative in this direction. And so what you're seeing here is that the voltage across here is positive, but the current's entering the negative terminal. So this is a different sign convention. So that means in this case here, what we're seeing here is we're seeing the voltage being positive, but the current this time is negative. So when I look at the power here, if I multiply V times I, you're going to see here that this guy is negative. So then, using the same language that I used up here, if the power is negative, then that means that the element is active. And what does active mean? It means it delivers power to the circuit. And that is the definition of an active element. Now note that this is really unsettling if you kind of think about this. And the reason why it's unsettling here is that imagine I have, well, a battery. I mean, that clearly, if you hook up a battery like you did in yesterday's lab or what you're going to do on Friday, that battery is clearly adding energy to the circuit. But let me ask you a slightly different question as an example here. Imagine that you have a capacitor. So I have 2 plates for a capacitor, right? So that means that in between here, I have some dielectric. And then this is my capacitor here. And what I'm going to do here is that I'm going to charge up this capacitor. So that means across this capacitor, it has some voltage across this thing. Now my question is this. Suppose I come here and I attach this thing in parallel to a resistor. Okay, so if I instantly attach it to the resistor, then I'm going to ask the following question. Does the capacitor behave as active or passive? Does the capacitor deliver energy to the circuit, or is it passive and absorbs energy?
That really matters. The type of current really matters there, doesn't it?
In this case, it's DC.
Okay, yes. So it is passive.
It's passive.
It absorbs energy, doesn't it?
It absorbs energy because the current goes from positive to negative. So capacitors as well as inductors are not active elements. They're passive. And I don't know if you really understand what I'm saying. You really won't start to understand until we get sort of like to chapters 6 and 7 and 8, where we're going to be dealing with capacitors and inductors. And it's a very, very hard conceptual thing. Very, very, very hard conceptual thing. But capacitors and inductors are not active elements, they're passive. So that means that the current has to go from the positive to the negative. And that's a story for another day, and we can talk about that.
Except just to lead into it, Carlos.
Just to lead into it, right?
Show the direction of the current in the resistor and the direction of the current in the capacitor with an arrow. Yeah.
Like that. And if they have that polarity and they're in parallel, they have to have the same one. So the currents have to go this way, like Jason just said. So check it out. We've been talking about energy. And so if I'm thinking about energy, then I must be talking about conservation of energy. And when we think about conservation of energy, we typically talk about the initial energy for the system being equal to the final energy for the system. But remember, energy is really, really difficult to measure, right? Energy is difficult to measure, but we know that energy is proportional to power. So instead of talking about conservation of energy, in circuits, we talk about conservation of power. So in circuits, we talk about conservation of power. And what do I mean by conservation of power? There's a couple ways that we can write this thing. Now, if you go online or if you look at textbooks, they're going to write it a different way. But I think we can say this here, is that when I think about conservation of power, what I really mean here is that I say here is that if I look at the total power that's active, it must also be equal to the total power that's passive. That means all of the energy coming from the active elements are passing that energy to all of the passive elements. And so what I typically write this as is I say all of the active powers, the sum of all of the active powers in the circuit must equal all of the passive elements in the circuit. And this is what I call conservation of power. But there's a problem here. And the problem here is that the sign convention here is that we ignore. How do I say this? The sign convention here is that if I have an element and I have current going like this, where this is a positive and negative terminal, then this element here, its power is passive. And if I look at this other element, and I have the same voltage, this element is active. But the issue here, you're going to find here in this course, the minus signs become horrendous. So these guys don't really have a sign when I'm doing sum of powers, because the way it really looks like is it looks something like this. Another way that we can write this is that we could just say all of the active powers minus plus all of the passive powers equals to 0. So automatically, I know that there's a minus sign for all active powers. So when I'm looking at this guy right here, right? So this is an automatic minus sign. And so when I look at this guy right there, this is really sort of like the magnitude of the power without the minus sign. So when I'm writing this, I've already accounted for the minus sign by putting it on both sides here. So before I move on to some examples, one of the things that I want to say here is that conservation of energy is not, the end-all statement for all of physics. Conservation of energy gives you a constraint on what a physical system can do. In order to answer detailed questions using conservation of energy or conservation of power, you typically need more information. And so one of the things that you want to be careful here is that you cannot use conservation of power to solve detailed questions about circuits. If you try to do that, you're going to run into problems because you're not going to get good numbers because you need more details in this thing. So you got to remember that. There's a statement in my lecture notes where I talk about a Newton's cradle. Like if you tried to use Newton's cradle to answer a question just using conservation of energy, in Newton's cradle, you can drop one ball. Conservation of energy says that I could get 2 balls to come out. But there's a problem. That's never observed in nature. When you apply conservation of linear momentum to that system, you find that if you use conservation of energy and conservation of linear momentum, you can only get the number of balls coming in as equal to the number of balls coming out. So conservation of energy is not sufficient to answer all the details on circuits. So what I want to do now is I want to go in and I want to lightly do this example. And the only reason why I'm doing this example is that my experience is that if I don't do this example and then you go to your homework, I find that people have a hard time dealing with lines. They sort of like forget how to deal with, solving the equation for a line. So let's go look at this thing here. So I have 2 examples back to back. So the first one says you have a current source, and a current source is very similar to a voltage source. It puts out a constant current, just like a constant voltage source puts out a constant voltage. But remember, I'm really misleading you when I say that. There is no such thing as a current source. There is no such thing as a voltage source. A voltage source has, if you say a voltage source, then it's not connected to anything. If I say a current source, then it's not connected to anything. Sources are power supplies. They don't just put out voltage and they just don't put out current. They put out both. So the appropriate thing to say to this current source is that it's a power supply that puts out a constant current. So when I say I have a voltage source, I could say that I have a power supply that puts out a constant voltage. And those are details that I'm just going to have to beat the hell out of you with them until you get them, because they're important details. So what you have here is that you have a constant current source. And what you have right here is that you have some load right here. This is the load. And what we know here is that this load, because there's a current drop across it, will have some voltage, so that we assume that these elements will have some voltage drop. And what they're doing here is that they plotted the current and they plotted the voltage. So the first part here is that we want to do what? We want to determine the power as a function of time. So what that means here is that I have to get the parameterization of the current and the voltage. So let's look at this thing. So when I look at this current, so in other words, what I'm really doing here is that this guy and that guy are functions of time. So when I look at this here, you could see, I look at the voltage and you could see that it's actually broken down in half a second intervals. Whereas the current is also broken into half a second intervals, but you could see that I also have current for 1 second and 2 second intervals where, really where there's the difference here. So the first thing that I got to do here is that in order to get the voltage and the current, what do I got to do? I have to parameterize the curves. In other words, find their equations. And what we know here, so if I start off with the current versus time curve, we know that when I look at this thing here, you can clearly see that up to 1 second, the current is constant, right? It's just 1 amp. However, you could see though that I have a linear line between 1 and 2 seconds. So what I'm going to do here is that if I think about a linear line, we all know and love this linear line equation. So now if I translate this into our equation, I'm going to have some slope and some intercept that I got to pick up as. So if I look at this guy here, we can clearly see that the slope has to be -1, right? So if I look at the slope for this curve, it should be what? The rise, which would be the current over the time. And then I'm going to pick 2 points here. So if I pick a point here and I pick a point here, I can get what that slope is. So if I look at that slope, you could see that the final is 0. It starts off at 1, and then I'm going to go from 2 to 1 second, and then clearly I have a slope of 1 amp per second. So I know that what my slope is here. Now, but that's only part of the equation. I have to get the intercept. When I look at the intercept, what I do here is I pick one point on the line. And I would say that the easiest point to pick on the line is the one at 2 seconds. So what I do here is that I pick one point on this line, and I'm going to pick it where t is equal to 2 seconds, which then tells me at 2 seconds that current is 0. So now that I have that, then I know that I at 2 seconds is of course 0. But if I look at my equation, it's going to be what? Minus 1t plus b, but of course t is at 2 seconds. So when I look at that, you could see here that tells you here that the slope, that the intercept in this case is plus 2 amps. So now I have my intercept and I have my slope. So therefore, the current I of t, in this case, it's going to be between 1 second and 2 seconds, must be minus t plus 2. And that's what my equation is right there. So now that I have my equation, what I can do here is that I could go in and I could not sort of like set up a table. If I set up a table, I'm going to do half a second intervals. And then I have, so if I look at this guy here, what you're seeing here, let me make sure then you know what? I'm only going to do half a second intervals just because of the voltage here. But once I get to 1, I'm going to go from 1 to 2 right away. So then if I go from 1 to 2 seconds, and then I'm going to go for anything for t greater than 2 seconds, then I could come in and I could just start to find my table here. And so if I do that, if I look at my current, well, I know that the current between 1 and 2 seconds has to be 1 amp. So then I'm going to come over here and I'm going to go, okay, so this is going to be 1 amp, 1 amp. And then between 1 and 2, we've already defined our equation, and that equation should be minus t plus 2. And then after that, we could see that the current goes to, looks like it's 0. So I've now done that. So of course I could go in and do the same thing for the voltage line. And if I do that and I parameterize these curves, you're going to see that just by looking at this thing, you could see that the slope is going to be 3 minus 0, 0.5 minus 0. So it should be 3 divided by 0.5 should give you 6. So you would expect that this guy looks something like what? 6t. And note that because if you do the same type of thinking that I just did, I now have what? I now have the current and the voltage. So now I could go get the power as a function of time. And the power is then going to be what? The current times the voltage. So the power should be 6t. And when I multiply the current times the voltage, it should be minus 6t plus 6. And then you could just go on and actually finish this right here. Now, one of the things that we got to do, though, is that in order to get the energy, we have to integrate the power, right? So to get the energy in the element, we know that power, and remember we use W for energy so we don't mix it up with electric field. So then this means here, if I want the energy, I have to integrate the power as a function of time. So if I pick out the first one here, you could see that that's a fairly straightforward here. So if I'm going between 0 and t, let me be careful here, where the power function is between half a second, then I know that for this guy here, I'm really integrating from 0 to t, 6t dt. And of course, that's a fairly straightforward integral, which then gives me 3t squared. So then I could come in here and I could write 3t squared. So that's roughly how you do that problem. Am I going to finish this problem? No. This was essentially a review to remind you that you have to get the linear line equations. So I'm going to leave the rest of this problem for you to do on your own. Okay, so now I'm going to move on to the next one that I want to do. And this one's the more important one. Okay, so when I look at this question here, so this is the one I want to do. Example 1.2. This is the more important equation or example here.
Pros, could you scroll up just for that last line of the last example, please? Thank
Yeah,
you.
not a problem right there. So it says, example 1.2 reads, conservation of energy requires that the sum of the power absorbed by all the elements in the circuit is 0. What I really mean by this statement is that if I look at the sum of total powers, this is really the sum of all of the passive minus all of the active elements. That must be 0. All of the energy produced by a power supply must be absorbed by the circuit. There's no leftover energy, ever. You would violate conservation of energy. But because of the sign convention, we said here that we're really looking at passive equaling the active elements. So this is the preferred choice. When you do it this way, there is no signs. So let's go look at this thing here. So my job here is to figure out if this circuit goes using conservation of power. That means, are these two equal? If there's, so if this is correct, and what I mean by correct, that means that all of the power absorbed by the passive elements must be equal all of the power delivered by the active elements, then the circuit has gone through the first check of whether it could happen or not. If this is correct, then the circuit is possible. Okay, so note that I have 5 elements, and circuits is going to try to trick you with the sign convention. So we got to be careful with the sign convention, okay? You got to be careful with the sign convention. So what you're finding here is that it goes something like this. So if I look at power 1, so the question is that now I have to determine active or passive elements. So let's look at 1. So if you look at 1, what I'm really seeing is that I'm seeing this guy right here, right? This is 1. So the first thing that you're seeing here is that without any doubt, here's the current. That's 2 amps right there. So in other words, I1 looks like this. Let's look at the voltage. So what the voltage reads is it actually reads plus minus 2 volts. But note, they've given you this extra minus sign. This is equivalent in voltage here, where that minus sign and that minus sign essentially flip each other around. So the equivalent statement here is that this guy actually is 2 volts with the opposite polarity. So then when I look at my element, it really looks like this here.
So that's an active element.
So in this case, it's an active element because it's coming in from the negative terminal. So therefore, we could then say that P1 is active. And how much power does it have? It has 2 times 2, which is then 4 watts. So then I'm just going to go around the circuit now. So if I start to look at this, look at 2. Because these guys are in series for 2, note that the current is going in that direction. So that current is entering the positive terminal. So therefore, I could immediately say that this guy must be passive because it's entering the positive terminal. So this guy should then be 2 times 5. It should be 10 watts. Let's go to 3. Look at 3. You could see that the current is entering what? The positive terminal. So then I could come over here. Where's my mouse at? There. I could then come over here and just say, okay, P3 is clearly passive because of the terminal here. And we could see that this is going to be 3 times 3, which gives me 9 watts. If I go to P4, I'm looking at the following thing here. Check out the current. Look how I'm trying to confuse you by putting a minus sign here. And note that on this guy here, this is a plus sign because I didn't draw a minus sign. So what this is really saying is that that -5 current is really what? It's really 5 amps going in that direction. So when I look at 4, you're seeing here that the positive 5 amps is entering the negative terminal. So therefore, 4 must be what? It must be active. So in this case here, it's going to then be 4 times 5, which is then 20 watts. And then finally, we get 5 here. And you could see that 5, when you look at the current, it's entering the positive terminal here. So therefore, it must be passive. So if I look at this thing, then element 5 is passive, which is 1 times 5, which then is 5 watts. So according to conservation of power, then the sum of all passive must equal the sum of all active. So if I do that, you could see here that passive elements are going to be what? P2 plus P3 plus P5 must equal all of the active elements, which is P1 plus P4. So if I start putting in my numbers, you could see that this guy's going to be 10 plus 9 plus 5. And this guy's going to be 4 plus 20. And you could see here that this guy equals what? 24 watts. This equals 24 watts. So this tells us here that according to conservation of power, this circuit has a possibility of going. That's what I mean by that. Okay, I'm going to move on and I want to go start talking about circuit elements. So now I want to go talk about circuit elements. So we just talked about the 3 variables, right? The 3 main variables: current, voltage, power. Now what we want to talk about is that we want to talk about elements, particular elements. And when I'm looking at this, you're going to find here is that this chapter is somewhat theoretical and it could get really abstract. My job is not to really do that. What I really want to do is I want to introduce the idea of a linear element. Once you have a linear element, what does it mean? And then the easiest linear elements to talk about are resistors and power supplies. But you're going to find here is that these circuits elements that we're going to be looking at, we're going to introduce a new type of power supply known as a dependent source. And these guys intuitively are going to be abstract, to say the least. So let's see if we can get to it by the end of this lecture here. So now we study linear circuits. Okay. What does it mean to be linear circuits? We study linear circuits, and that implies that these guys are really low voltage circuits. And when you have a low voltage circuits, then what you find here is that Kirchhoff's laws, right? Kirchhoff's voltage and current law, Kirchhoff's laws are valid. Now, a very common model that people typically use here is they use sort of like a water flow to talk about what actually happens in a circuit. Water flow models of circuits are limited in what they can do here, but it's not really true, if I could say that. Like, let me give you an example. In physics 4B, I'm pretty certain that they told you that current occurs in a circuit because of the battery, and only the battery that you hook up to the circuit. It turns out that that's not really true, that the battery is not enough to create current in a circuit. You'll find here is that there's these things called surface charges, and surface charges is absolutely required in order to make current flow in a circuit. But I mean, clearly the battery is important. And so what I'm saying here is that depending on the model and how you model elements, you'll find here is that when we talk about a linear circuit, we're really saying something very, very specific. We're saying low voltage, and if I have low voltage, then Kirchhoff's laws are valid. If you do not have these situations, you have no choice to go to Maxwell's equations and then to solve these equations. So there's no choice here. So the two elements that we really want to talk about here is that the two elements we will talk about are resistors and power supplies. Now, the question is, how do we model resistors? Okay, so when I think about resistors, we say that resistors are modeled by two laws. The first one is clearly Ohm's law, right? So when you're thinking about Ohm's law, you automatically know that the resistance is modeled as the voltage divided by the current. And another way that you can model here is that you use the definition of resistance. And so when I look at resistance and I look at the physical characteristics of resistance, we know that the resistance is really proportional to what? Well, assuming that there's not too much heating, we talk about the resistivity, the length of the resistor, and then the diameter of the resistor. And so even though you defined it this way, it turns out that that's really not a good model to really tell me what do I mean by a linear model. A linear model has a very, very specific definition without any doubt. And linear elements are defined by two underlining principles. And it just happens that you look at Ohm's law and it's linear, right? You go like, yeah, you can see that there's no square parameter or sine parameter. So you're going like, of course it's linear. And I'm saying that's not true. Ohm's law doesn't come first. What comes first is these two principles. So one of these principles is called superposition, and the other one is called homogeneity. Now, homogeneity, I'm not going to go over, but what you find about homogeneity is that it's a scaling law. Okay, assuming I spelled homogeneity correctly, but we're among friends, so we're probably okay with that. So let's go talk about superposition, because I think superposition is important. So when I look at superposition, here's what it is here. So all linear elements follow the principle of superposition. And what I'll do here is that I'll give you an example and not try to get into too much details here, but let's think about the following thing here. What you find here is that imagine that you have a circuit like this, okay? So suppose that you have a circuit that looks like this. So I have some element here, and then maybe I have a voltage source, and when I have this element here, I have this other element here, and then here I'm going to say that I have some voltage source, which I'm going to call V1. Okay, so V1 is a voltage source, but remember what I said when I say a voltage source, it's a power supply with constant voltage. That's what I mean when I say voltage source. So what happens here is that because of this voltage source, I'm going to get some current here across this resistor, which I'm going to call I1. So in other words, voltage source V1 causes current I1 through the resistor. So good so far here. Now, one of the things that I said here is that resistors and power supplies are linear elements. What do I mean by linear elements? Well, that means that this voltage is proportional to that current. They have to be this way. Now, suppose I add a second power supply. And I could add it anywhere I want. I could make it as complicated as I want. So what I'm going to do here is that I'm going to come in here and I'm going to highlight this guy and make a copy of it and just bring it down here. I know I'm probably pissing some of you guys off, but it's okay. So what you want to do here is that, look what I'm going to do now. I'm going to come in here and I'm going to add another piece to this circuit. So I come in here and to try to complicate it, I'm going to add another element, and now I'm going to add another power supply, V2. So what you're seeing here is that it looks like this. Now what I'm going to do here is I'm going to ask, what is the current through that resistor? Well, because superposition is valid for linear elements, or elements follow superposition. What you find here is that the current, you still have the current that's produced by V1, but now there's an additional current produced by V2. So when I look at that, there's a second current that looks like this. So what superposition says that if I have V1, it's going to produce a current I1. If I suddenly add a second voltage source, because it's linear, it's now going to be proportional. These two voltage sources are then going to have a current that's going to be proportional directly to these voltage sources. The fact that they scale this way implies that the voltage source is a linear element. And by the way, I could do the same thing with the resistor. If I have a resistor in an element, and then I measure the current, if I increase the resistance, then that current will change according to that resistance in the circuit. Now note, by the way, that's not true for capacitors and inductors, because you have, unless you go into phasor form. But if you're using differential equations, that's not the way they behave. They're not linear elements. So,
Hey, Carlos.
yeah.
Oh, sorry, quick question. So does this superposition apply no matter what the other elements in the circuit are?
For power supplies, yes.
That's cool.
But if for capacitors, no.
Got it. Thanks.
So that's why capacitors and inductors are not linear elements. They have a completely different dynamic. Now note, we could have just said, yeah, it's linear. Resistors are linear because they follow Ohm's law. I agree. But wait a minute, let's step back just a little bit. Not all resistive elements are linear. If you look at a light bulb is linear when it's cooling off or when it's not too hot, but if it gets hot, it's logarithmic. So a light bulb is not a linear element. A resistor is a linear element because it does not change appreciably as you increase the current through that resistor. But light bulbs are not linear elements. So
But if you got a resistor, if you ran enough power through a resistor, it would heat up and become nonlinear. And that's
yeah. It's actually what really, well, I don't really want to jump into this. It's probably the most dominant thing about resistors is, believe it or not, it's not so much current, it's actually frequency dependence. As you go to ultra high frequencies, what you find is that resistors are not linear at all. And so, but that's beyond the scope of this conversation. So then what I want to go do here is that then let's go look at resistive elements, right? And so what do we know here? So Ohm's law is clearly linear. And what do I mean by clearly linear? Plot the thing, right? If you plot this guy, and this is current, and you plot this thing for a resistor, it's linear. We know that that slope is equal to 1 over r. That's a linear line. So clearly, when I look at this thing and I talk about Ohm's law, we could say then that resistors are linear and passive. What does that mean here? Well, I know that the voltage across a resistor must be given according to this law right here. And the power of a resistor should be the voltage times the current here. But I can rewrite this using Ohm's law. I can also write this as VR squared over R, or IR squared over R. So when I talk about linear elements that are resistive, they must follow this thing. And note that all of these powers must be passive. So I got to keep banging you with the sign convention, because you don't have to trust me. Jason's in the room. I'm going to go after you like crazy with plus and minus signs. And you'll probably hate me for a while. And that's a good sign, not a bad sign. So as I've been saying for frickin' decades now, if you don't know your plus and minus signs, you don't know shit. It's that simple. And when you get, 8 equations, that you got to solve, 8 simultaneous equations, if you get one sign wrong, you're screwed. You're going to be chasing shit. You got to get your plus and minus signs right. So let's start with this example here. This is an example that you're going to say is there's something wrong about that. And this example is purely here to make you uneasy with minus signs, because I got to desensitize you on minus signs. That's my number one job. So here we go. Let's go do it. So what you're finding here is that you have a voltage source, right? And as I have this voltage source, what I want to do here is, it says they're connected in parallel. That means that right? If they're connected in parallel, that means that I have 2 lines like this. And so if the voltage of this source is 150 volts, what this really means is that down here, it's customary. I don't have to do this. I call this the ground, which I call 0 volts. And up at the top, I call this 150 volts. By the way, I could have called this up here 350 volts. And I could have called this guy 200 volts, and that's totally legit. But what's customary is to call the negative terminal 0 volts. Why? Because it's easier. That's the only thing here. So what we want to do here is that our goal here is that we want to calculate the current through each resistor, and we want to calculate the power absorbed to each resistor. So let's go do that. So the first thing that I want to do here is that I'm going to calculate the current and the power of each resistor. So we want to get the current and power of each resistor. So when I focus on resistor 1, we can clearly see that, look at this. Here's the positive terminal. So that means here that this is the positive terminal right here. This guy down here is the negative terminal. How about if I do this in red to make it a little bit clearer? So when I look at resistor 1 now, what I'm really seeing is that I'm seeing this. This guy here is my positive terminal. That's my negative terminal. But look at the current. The current is going this way. So if I calculate the current for this 50 ohm resistor, what we say then is that according to Ohm's law, we then go in and we just say, well, I know that I1 must be the voltage across 1 times divided by the resistance of 1. But we know that since they're all parallel, they have to have 150 volts. So when I write this in, this is going to be 150 volts divided by 50 ohms. So therefore, I should have a positive 3 amps for current 1. right? That is absolutely true. So I know that that current is positive. Why? It enters the positive node. So now if I go calculate the power, we could say that the power of 1, well, should be the voltage of 1 times the current of 1. And when I look at the power, you could see here that the voltage is in the positive direction. So then this means here that this is going to be plus 150 volts. Note that the current is entering the positive terminal. So this guy is then going to be what? It's going to be positive 3 amps. So therefore, this gives me positive 450 watts. And note that that's greater than, let me be careful. I'm going to write this as P1, and no surprise, it's positive, which then tells me that this thing is passive because the power is positive. The current is going through the positive terminal. What about resistor 2? Well, one thing that you see about resistor 2 here is that this little SOP is going upstream. And you're going like, oh, they made a mistake on the problem. And the answer is no. The problem is set up correct. So what you're seeing here is that when I now look at resistor 2, when I look at this guy, the sign convention here is that look at that current I2. So what this is really telling me is that the current I2 is going upstream. And if it's going upstream, this immediately tells you that there's a sign problem, right? The current must be negative in this case here. So if I look at this guy here, this guy is now 25 ohms. And if I look at this guy, according to this Ohm's law, I could then come in and just say, I still have this guy here, but because it's going upstream, I have to do what? I have to include a minus sign because it's going in the opposite direction of the other one. So when I look at the numbers of this guy, you could see here is that this has to be what? Negative 150 volts, 25 ohms. I'm going to get minus 6 amps for the current 2 here. Okay, but wait a minute. Let's look at the power. So what this really tells me, I should have said this beforehand, this really just says here is that this resistor does not follow the passive sign convention. That's what it tells me here. But resistors are passive. The power better be passive. So let's go look at this thing here then. So now, if I look at the power of this guy, the power is really what? V2 times I2. The very first thing that you want to pay attention to is look at the terminal that the current is entering. It's entering what? The negative terminal. So automatically, when I'm looking at this, I have to put a negative sign there because it's entering the negative terminal. So then I come in here and I get a minus, and then we know that the voltage then is 150 volts. But wait a minute, the current that we calculated was what? Minus 6 amps. So when I look at this guy, I get positive plus positive, which gives me positive 900 watts. But when I look at this power, that power is what? Positive. In other words, even though that thing is not following the sign convention, this resistor is still passive. Exactly like we expected. Okay. Here we go. Let's move on to the next thing. We want to talk about sources now. So the next thing that we got to talk about is that, so we want to talk about power supplies. And power supplies essentially come in 4 flavors. What I mean by that, there are power supplies that do what? They are independent and dependent sources. So there's going to be 2 kinds. And when you look at these guys, power supplies can also be passive or / and active, depending on the circuit here. So the whole idea here is to tell you that there are 4 different types, there are 4 varieties of power supplies. So the first thing that I want to talk about is I want to talk about independent power supplies. And sometimes what you'll see me is that I'm just going to drop the word power supply because I got to get it into your head that a voltage source is a power supply. A current source is a power supply. So a lot of times you're just going to hear me say a source. So let's go look at that. So sources come in 2 flavors. There are voltage sources. So when I think about voltage sources, I can have an active source. And what do I mean by an active source? That means that the current goes where? It enters from the negative terminal. So this source here is active. But I can also have passive sources. So if I have a passive source, then that means that the current must be coming in through the positive terminal. So then this would be a passive source. Now, a new source that you most likely do not know what it is called a current source. And once I explain in detail what a voltage source is, a current source will make more sense here. And so how do I define a current source? Well, a current source will supply current to a circuit here. So it is clear that the source current is flowing. How? It's flowing upwards here. So the question is not the direction of current, but the polarity of the voltage here. So this is an active current source. So if the current enters the negative terminal, then this is an active current source because the current's entering the negative terminal. On the other hand, if the current enters what? The positive terminal, right? Then this source here is passive. And those are going to be really important distinctions that you're going to have to master here. Okay? So now let's go talk about independent sources here. So if I was to give you a very naive definition of an independent source here, I would say that an independent source does not depend on other circuit variables. It does not depend. So one very, very, very simple example that we could imagine here is that a 9-volt battery. So let's talk about examples here. So one example would be a 9-volt battery is a, how do we say that? An independent voltage source. Okay. So what this implies here is that its voltage is fixed at 9 volts, regardless of the resistance or the current in the circuit of other variables like resistance or current. So what do I mean by this here? So what I mean by this here is that if I look at this thing, you could imagine that I have 9 volts. And what you're going to see here is that imagine that I come in here and I put a load on this circuit right here. Right? So this is my load here. So what you find here, I know that this 9-volt battery is going to produce some current here. But what happens if I change the load? So if I have a changing load, let's say it goes from R equals to 1 kilo ohm to, let's say, 5 kilo ohms, note that the current is going to be variable. Depending on how I change this, you're finding here is that the current here is variable. So in other words, a 9-volt battery always keeps its 9-volt value, but its current is constantly changing. So how do I say this here? So in other words, a voltage source is a variable current source. And remember, what is a voltage source? A voltage source is a power supply with a constant voltage value. But remember, power supply means what? That there's a voltage times a current. So even though we say voltage source, you got to remember it's a power supply. It produces both of these things. So a good definition of a voltage source is exactly this. A voltage source is a variable current source. It's both. It keeps the voltage constant, but the current varies in the circuit depending on the load. Now, let's go to a current source here. So over here, I talked about as an example as a 9 volt. So now I'm going to say as another example, I'm going to say, what if I have a 5 amp independent current source? If I have a 5 amp independent current source, what that means here, very similar to what a voltage source here, it says here that its current is fixed at 5 amps regardless of other circuit variables. So what do I even mean by that? So when I look at my current source, let's say that it looks like this guy right here. This is 5 amps. And now I'm going to put a load right here. Right? So this is my variable load. Now, when I look at this guy, what am I actually seeing here? Well, I know that the current that this guy is always going to stay 5 amps. But wait a minute. If this is always going to stay 5 amps, what happens then if I change my load now? So my load, so I now have a changing load. And before I just said, what if I change this load to 1 to 5 kilo ohms? Well, think about it. If I'm going to get 5 amps regardless of what happens, what this means here is that the voltage across the current source must be a variable voltage source. So that means here that, so then this guy right here is a variable voltage across the current source. So in other words, if I have 1K, so if I have, let's say this is 5 amps, and I put 1K right here, if I'm going to keep this at 5 amps, then according to Ohm's law, the voltage across this guy has to be what? Well, it has to, it's going to be high because that's a kilo ohm resistor. So it's going to be what? How much is that going to be? Well, according to the voltage here, Ohm's law says that the voltage then has to be R times I. So that's 1,000 ohms times 5. So it's got to be 5,000 volts. Okay, so that means this guy is going to be 5,000 volts. But what happens if I change that thing to 5 kilo ohms? Right? So now I change to 5 kilo ohms. Right? If I change that to 5 kilo ohms, look what happens. That current source is still going to be 5 amps. The only way you're going to get 5 amps like that is if the voltage does what? It changes. So this voltage now goes to 25,000 volts. So that means that current source is changing its voltage across that. So in summary, right, here's what we could say, that a current source is a variable voltage source. So they behave, very, very, very similar, but they mean different things. And, I've heard people say, really? A current source is not really a voltage source? But you're getting stuck on sources being either current or voltage. That's not correct. They're power supplies. They produce both things here. Uh-oh, I think I'm over. So, hey, I'll upload this a little bit later today. Now note that I'm in lab till like 5:30, so it's probably not going to be till tonight when I upload these notes and the video. So,
Carlos,
yeah,
is the video from lab yesterday uploaded already?
yeah, I uploaded it already.
Okay, cool.
And note that initially I put the quiz and homework for Monday, but note that I switched it to Wednesday online. Okay? Okay, man. I'll see you guys later.
All right, thank you. Have a
Okay,
good one,
take
Carlos.
care. You too.
Thanks, Carlos.
Thanks, Carlos.
Thank
No
you,
problem.
Carlos.